Okay, let's do the third video, trig limits, and I've dubbed this one Part 3, the fun ones. Okay, and this just takes a little bit more strategic initiative and sort of instincts in order to make these work. I'm going to do 3 examples. The first 2 are going to be relatively simple. The last one is going to probably make you groan, but you can go ahead and skip the third one once you see what it is if you want. I think it's kind of neat. So let's go ahead and get started. Now, is this indeterminate? Yes, it is, okay? Because sine of pi is 0 and pi minus pi is 0. But I have a problem. X is not going to 0. But I do know that the numerator is going to 0, the denominator is going to 0, so it's kind of similar. And what you need here is you need sort of a swapping of variables, okay? So we're going to go ahead and let y equal pi minus x. So what we're going to do is we're going to use this to transform this into a separate variable, and hopefully by doing that we can get it in the form that is much like the ID, okay? So I know that sine of x winds up being, if you go ahead and sort of flip these around, x is equal to pi minus y if I solve for x, right? So I add x to both sides and then subtract y from both sides. So I can get pi minus y over y. Okay, well at least I've gotten the denominator down to a monomial, okay? Now, as x goes to pi, y goes to pi minus pi, right? So get that? As x goes to pi, y goes to pi minus pi, right? Or y goes to 0. So once I've changed that, I now have the denominator in terms of a monomial. I now have this in terms of a monomial. The question is, how do I get this numerator to become just sine y? Now, I could use sum and difference identities, or I could just remember my transformations, right? You obviously, just remember this, if you have y is equal to sine of pi minus x, isn't that equal to sine of negative x minus pi? If you just factor out the b value, remember the b value in terms of transformations? And of course, since sine is odd, I can pull that negative out in front. Well, I don't actually pull the negative out in front, but you understand what I'm saying because of odd identities. It's an odd function, right? Now, what happens to sine when you shift it to the right half a period and flip it over the y-axis? See, there I use the word flip. You guys are such a bad influence on me. What happens when I shift it to the right by pi and reflect it over the y-axis? Well, it winds up being right on top of itself, okay? So that winds up being synonymous with sine x. Now, of course, I did this in terms of x, and this is in terms of y, but the same principle applies. And so I get the limit as y approaches 0 of sine y, which is synonymous with sine pi minus y. And now it all of a sudden is in terms of my identity, and I can go ahead and simplify that into 1. So that was fun. Let's go ahead and do this one right here. This one might actually be just a little more straightforward. Okay? Well, yes and no. We'll see. The same strategy is going to be employed here. Okay? I'm going to use a replacement variable. And in using that replacement variable, I just have to do the same move. Let y equals, but instead of pi minus x, I'm going to call it pi over 2 minus x. And then, of course, again, I'm going to have to solve for x. And so I know that this is synonymous with this. In order to get from here to here, all I have to do is just add x to both sides and then subtract y from both sides. So I know that this winds up transforming this into cosine of pi over 2 minus y over y. And of course, as x approaches pi over 2, y approaches pi over 2 minus pi over 2, or it approaches 0, right? Now, this is really only one step away from being able to solve it, because I should recognize that as an identity from last year. What identity is that? Well, it's a cofunction identity, right? That's the whole meaning of co. Cosine is complement of sine, or complementary sine, right? And therefore, you can go ahead by your cofunction identities and turn that straight away into sine y over y, and therefore that is equal to 1. Cha-ching! Okay, so those were two nasty ones that dealt with replacement variables and substituting in. Let's go ahead and deal with one that's just a little bit more robust, I guess you should say. Okay, and I actually solved this one for not a former student, but a former student's older brother, who emailed me from college at his sister's behest, and basically needed this for one of the homework sets that he was given up at A&M. And I thought it was such a great problem that I went ahead and typed it out, and I sent him the solution. I think by that point he had actually solved it, but thanked me anyway. But I thought it was so neat that I went ahead and saved it, and I'm going to share it with you guys. So the limit, and that's x approaches 0 down there, if you can actually. Let's see if I can get the camera a little bit closer. Yeah. Okay. So we see the fact that it's the limit as x approaches 0 of sine mx minus sine nx. Actually, it's a little too small. I tell you what, I'm going to go ahead and reproduce it by writing it out. Okay? Now, we have the limit as x approaches 0 of sine mx minus sine nx over x cubed. Okay? Now, I know that I could split that up into two separate limits. Okay? But the problem is if I split it up into two limits, I'm going to get sine mx over x cubed and sine nx over x cubed. Well, that, once you pull the x out of the x cubed, you're still left with x squared, and so you're going to wind up with infinity minus infinity. Well, infinity minus infinity is still an indeterminate form, so you have to find a different way to change the form of this rather than separating the fractions, rather than pulling them apart according to their sum and difference, okay? And what we're going to do is we're going to go sum to product, okay? Now, if you don't remember sum to product IDs, don't sweat it, okay? I barely remember sum to product IDs, and I'm the teacher, okay? There's a reason why that test, when I gave it to you, was much easier, because quite frankly, you just don't run into them quite as often, and they don't really have the same utility that the fundamental IDs do, the cofunction, even the odd, the Pythagorean, or all that sort of fun stuff, okay? The sum and difference and the double angle identities wind up being very, very helpful as we're going to progress through this year, but sum to product and product to sum, not really that big of a deal. Okay, but we do see what's happened here, correct? Okay, well here's the thing. When I plug in 0 here, this is going to be cosine of 0, because that numerator right there, the mx plus nx, is going to be 0. So cosine of 0 can actually be pulled out, and I don't really even have to deal with it. And that 2 is a numerical factor, so we're going to go ahead and pull that one out. Okay? So let's get cosine of mx plus nx over 2. I know that this sine expression is going to require one of these x's. But the other two can just sort of come along as 1 over x squared. And then I'm going to have sine, and I'm going to go ahead and factor the x out of here, okay, just so that it looks nice and tidy. M minus n over 2, and that is my angle measurement expression. That is its coefficient, okay? So, if I'm going to deal with that as the coefficient, and I'm going to go ahead and include that down here, I need to go ahead and also multiply by that over here. And if I multiply by that over here, the 2's obviously go away, okay? And what I get here is I get m minus n times the limit as x approaches 0 of cosine mx plus nx over 2 times 1 over x squared times sine of m minus n over 2x over m minus n over 2x. Now this right here, when you plug in 0, is going to be 1. We've already talked about that, right? This one, when you plug in, is going to be 1, okay? Because the coefficients match, and that's our identity. The question is, what happens with this bad boy, okay? Now that one right there, as x approaches infinity, you should remember the shape of that. And if you don't, I'll go ahead and give you a heads up. The shape of that graph looks like that. So what happens as x approaches 0 for that graph? Well, it goes to infinity, okay? Okay, so it doesn't matter what this and this are, as long as they're not 0. I get m minus n times 1 times 1 times infinity. That limit goes to infinity, okay? Now, if you followed that, you're golden, okay? So I hope that that was clear and illuminating. Probably not as much fun as I promised, but of course my definition of fun is quite a bit different than yours, which is why I wound up as a math teacher to begin with. But I hope that these 3 videos on trig limits have been helpful. Shoot me an email, give me comments if they are not, or if they're still problems that you found troubling or a little bit too difficult, and I can of course do another video to supplement these 3.